section 1.2. You'll find we go through a lot of sections in a 2.5-hour class. So we talked about our outcomes. Sometimes though we want to make it a little more interesting, we might want to look at, say, a set of our possible outcomes. Okay? And we call these events. Okay? Or our events are a subset of our sample space. Now, I don't know if you guys know what subset means. It depends on which math classes you've taken. Subset would just be a smaller set. So our sample space is the entire set of all of our outcomes. So a subset would just be part of all of those outcomes. So in example 8, let's say we want to toss a coin twice. What outcomes are in the event A, which is defined as exactly one head? So let's remind ourselves, we've already done this. Our sample space for tossing the coin twice was we could get heads heads, or heads tails, or tail heads, or tail tail, which we do the tree diagram to find that and make sure we don't miss anything. So now let's look at our event A. A is exactly one head. So which of those outcomes have exactly one head? Well, not heads heads, but head tails has one head, and tail head also has one head. So those are the outcomes that are what we're interested in. We're only interested in things with one head, and there are two possibilities for that. Or let's say, for the next one, what outcomes are in the event B, which is outcomes with at least one tail. So at least one tail. Head head wouldn't apply, but we could do head tail, or tail head, or tail tail. And if you want to find the probability of an event, you would just sum up the probabilities for each outcome that went with your event. So like for B, I would just sum up the probabilities for each one of these three things, and that would give me the overall probability of at least one tail. So let's try it out. So my husband thinks that the perfect number of children to have is 2. So it turns out I first wrote these notes before we had kids. And we now have 2 kids and another one on the way, so I guess we're not stopping at 2 kids. But just to tell you that if I call random breaks that seem like a weird time, that's probably why. Okay. So let's keep going on this problem though. Let's say we want to have 2 kids. Let's assume that the probability of having a boy is the same as having a girl. Now I know biologically speaking it might not be exactly 50-50, but let's go with that for this class. Let's find the sample space and the probabilities of each sample space outcome by drawing a tree diagram. So for my first child, I can have a boy or a girl. Now if I have a boy first, I can still have a boy next time or a girl. And if I had a girl first, I could still have a boy or a girl. And that should be all of my options, right? There shouldn't be anything else left. So my sample space would be boy, boy, which is what we ended up with, boy, girl, girl, boy, or girl, girl. Those are all of my options. Now let's find the probabilities of each one. So the probability of boy, boy would be, what do you guys think? If having the probability of a boy is the same as a girl, should any of these outcomes be more likely than the other? They should all be equally likely, and how many outcomes do we have? 4. So each one should be 1/4. So probability of boy, girl, 1/4. Probability girl, boy, 1/4. Probability of girl, girl, 1/4. Now when you're done, double check. Are these all between 0 and 1? Yes. Do they add up to 1? Yes. So let's continue our example. These were the probabilities of each possible outcome. Now let's make it more interesting by finding the probabilities for each event. And when I do these, I always write out, okay, what outcomes actually correspond to what I want. So let's say we want to have 2 boys, or the probability that we will have 2 boys. So 2 boys, the only way I can get 2 boys is by getting BB. And that probability up above we wrote down as 1/4. So that one was easy. Now if I want to have 1 boy and 1 girl, so we'll say 1 boy and 1 girl, which outcome corresponds to this? So what has to happen for me to have 1 boy and 1 girl? Notice, did they say which order? No. So what has to happen for me to have 1 boy and 1 girl? Go ahead. Ooh, okay. So 1/16, so you're going to multiply them. Can you first tell me which outcomes, so just say like BB, BG, etc. Tell me which things will give me 1 boy and 1 girl. Okay, so BG or GB. Now, I wrote an or here, and I want to call your attention to it. So I just kind of said or naturally. Is or the right word to put there? Okay. I would say yes, right? Because I could get a boy-girl or a girl-boy. Either way, I don't need both to happen. I just need one of those things to happen. Okay. So that's an or, which will become very important later on. Okay. So now let's go back up to here. So the probability in an event is we're going to sum, which means add all the probabilities of the outcomes that correspond to the event. So we want to find the sum of all of these possible outcomes that go to what we want. So in this case, boy-girl was 1/4, and girl-boy was 1/4. So we would actually have 2/4 or 1/2. So our first response was a multiplication, and we will actually at some point tonight get to where we learn how and when we multiply our probabilities. But in this case, when it's an or, anytime you see an or, we're always going to be adding. And number 3, we will have at least 1 boy. So the probability of at least 1. Now it might seem like I'm writing out maybe more than I need to, but this is how much I want to see written out on yours. You should always be writing, this is the probability of what I'm finding. And then again, I always write out which outcomes actually go to that. So if I want at least 1 boy, we could again have boy-girl, or girl-boy, or boy-boy, right? All of those would give me at least 1 boy. So we would have 1/4 plus 1/4 plus 1/4, which equals 3/4. So you have a pretty high chance of getting at least 1 boy. And that's probably our most complete problem so far. So break in if you have any questions. Actually, before we turn the page, go back 1 page. I forgot I wanted to do a nice little diagram. So at the very top, this is the way we're going to draw it because this will be useful for our next thing. We usually draw just by convention, tradition. The first person that did it got a pick. He drew a big rectangle first. And the entire rectangle will be our sample space S. And inside this sample space, you have all your different possible outcomes. So all of these would represent your different outcomes. And inside that, you would have your subset of the outcomes you're interested in, which would be A. So with that in mind, and how we traditionally draw it, so S is the entire sample space, and A is what we're currently interested in. Let's go on to this next thing, which is called the complement. This is often something very useful. So we start with our sample space S, and we have some event A. Now maybe this event A was getting heads, at least one head, or maybe it was getting 2 boys, whatever it might be. So you have A. Sometimes you're interested in all the outcomes that are not in A. So in our situation here, if A was everything inside the circle, what is everything that's not inside of A? Well, it's all the stuff in the rectangle outside of the circle. So this red would be A complement, or A prime. Depends on which book you're using. I think our book uses the A prime more often. So in our case, again, A prime would be everything outside of A. And so this could be something like if A equals, trying to think of a simple one. Let's say that S equals tossing a coin so you get heads or tails. Okay? And let's say A is heads, then A complement would be tails. Right? It's everything but what you're interested in. Now, to find the probability of A prime, you'd have the probability of A plus the probability of A prime has to equal 1, right? Because everything has to add up to 1. So that means anytime you want to find the probability of A prime, the probability of A prime is going to equal 1 minus the probability of A, which we used back on what, the first page, when we said the probability of a biased coin was 0.3, so probability of the other side was 0.7. And this is called the complement rule. We'll use it all the time. So for our example, here's a probability model for color preferences. So probability that 0.42 someone likes green, 0.14 that someone, oh sorry, that was blue, 0.14 someone likes green, etc. So let's see, what is the probability that a person's favorite color is blue, purple, or orange? Okay, so probability of blue or purple or orange. So again, we said just sum up all the probabilities for each thing that we're interested in. So we want blue, purple, orange. So 0.42 plus 0.14 plus 0.05. Which would be 0.61. And number 2 is, what is the probability that a person's favorite color is not brown? Okay, so notice, pay attention here. They said not brown. There's 2 ways you could do this. Could you go through and circle everything that is not brown? Okay, so everything that is not brown would include all of those colors and all of these colors, and I could add all of those up. But that is going to take a while. Okay, what could we do instead? So go ahead.
Subtract brown from 1.
Okay, subtract brown from 1, right? So this would be equal to 1 minus the probability of brown. So 1 minus 0.03 equals 0.97. Now, again, you could go through and add up all of the other probabilities. It's just going to take a lot longer. And that's what the complement rule is for, to save you time. Usually you can do it the other way. It just saves you time.
Professor,
Yes?
are we just assuming that all the other ones add up to 1 then?
Oh, okay. Well, it did say it's a probability model, so we can probably assume that they do add up to 1, but you could check it. Usually we only check it if they say go ahead and check if this is valid. Everything else in your textbook, if it doesn't say check, it will be valid because they are supposed to add up to 1. But it's always a,
Okay, thanks.
yep. Okay, so in our next example, let's say we're playing a game that requires we roll 2 dice. Okay, and we're hoping to get 6s. Okay, so 6s are the good thing in this game. Now, as you're going through and trying problems like this, you always need to be organized, or you forget things and you get the wrong answers. So what I did is this is our actual sample space S, everything inside this box here, because I could get, say, a 1 and a 2, 1 and 1, or 1 and a 2, or 1 and a 3, or I could get like a 2 and a 1, 2 and a 2, 2 and a 3, etc. So I have listed out all of the possible outcomes. And again, it's important that I list it because there are 36 outcomes. If I'm just trying to do these off the top of my head, I will probably forget one. So let's go through first, and let's circle the outcomes that are in the event C. So we're defining C as rolling at least 1 6. So go through and circle everything that has at least 1 6. So everything over here and everything on the bottom, right? Those would all have at least 1 6. 6 and a 1, 6 and a 2, 6 and a 3, or 1 and 6, 2 and 6, etc. And sometimes this is the easiest way to do these problems, is list everything out and circle what you're interested in. So let's find the probability of C, or probability of at least 1 6. So what would I do here? What is this probability going to be? So let's start with this. What number should I have on the bottom in the denominator? Oh.
36.
36, right? There are 36 possible things. And let me ask you here, should the top say 11 or 12? 11, right? Because we don't want to count that last one twice. It's still only one thing. So there are 6, 7, 8, 9, 10, 11. There are 11 possibilities that give me what we want, so 11 out of 36. You always want to make sure that you're not double counting. Don't ever count the same thing twice. Now let's go with what is C complement in words. So there's your little prime. So if C is at least 1 6, what's the opposite of at least 1 6? Not rolling a 6, right? So no 6s. And to find the probability of C complement, you'd go through and you'd say, okay, everything that doesn't have a 6 would be this stuff right here, right? You could count all of those, add them up, and see how many possibilities that is. Or we could use the complement rule. So the probability of C complement is going to be 1 minus the probability of C, which we just figured out is 11 out of 36. So 1 minus 11 out of 36 gives me 25 out of 36. Or if you counted, you notice that it's 5 by 5, so there should be 25 ways to get what I want of no 6s. Oh, sorry, that was supposed to go on the next line, wasn't it? There you go. And we've done so well. Let's now try something that we do it 3 times, so make a bigger tree diagram. Let's say that we were going to have a quiz, which we don't actually have. But if we did, we had a quiz with 3 true-false questions, and you didn't study. Okay, so let's assume you didn't study at all, and you're just blindly guessing at each question. Let's find the sample space and the probabilities of each sample space outcome, and draw a tree diagram. So on my first question, what are your two possibilities? You could be, sorry, I think someone was going to say something. You could be right or wrong on your first question. And then no matter what you got on the first question, if you were right, you could still be right or wrong. But if you were wrong, you could still be right or wrong on the second question. And for the third question, you could be right or wrong, right or wrong, right or wrong, right or wrong. So again, a tree diagram just helps you be organized so you don't miss anything. So our possible sample space outcomes, I could be right, right, right. I could be right, right, wrong. Right, wrong, right. So go ahead, finish filling these in on your own. It's probably easier than trying to listen to what I'm saying. So when we're done, we should have 8 possible outcomes. Now, if you are blindly guessing and it's true or false, what should be the probability for getting something right? So just one question right, the probability should be 1/2, right? It's just equal chances. And so is there any reason that any of these branches should be more likely than another one? No, they should all be equally likely. And so if they're all equally likely, then the probability for each one should be 1 out of 8 because you do have 8 outcomes. So each probability would be 1/8. So again, each one is 1/8. So let's look at which outcomes are in the event that you get at least one question right. So looking at my list of possible outcomes, I want to get at least one question right. So instead of list them all out, so I could have right, 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 wrong, right, right, nope, right, wrong, right, right, wrong, wrong. So you can do this on your own too. Wrong, right, right, wrong, right, wrong, 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 right. And hopefully you can see why you really want your tree diagram, because if you're just trying to spit this off the top of your head, you would probably miss one. So these are all the ways that I can get at least one question right. Now, what's the probability of getting at least one question right? So we listed all the ways to do it. So the probability of at least one right is you just add up the probability of each one of these. Each one had a probability of 1/8, so it would be 1/8 plus 1/8 plus dot 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 up to 1/8. How many of those 1/8s did I have? 7 of them, so 7 out of 8. But of course, we don't actually like having to list out 7 different ways to do something and adding up all the probabilities. So we could use instead the complement rule, okay, as a different way to get the same answer. So the probability of at least one right is equal to 1 minus the probability of. Okay, so again, we are going to do this so many times in this chapter. Anytime you want the probability of at least one right, what is the opposite of getting at least one right? The opposite of at least one will always be none. Okay. And so we could do 1 minus the probability of getting none right. Which event actually has none right To get none right, you'd have to get wrong, wrong, wrong. And that has a probability of 1/8. So 1 minus 1/8 is 7/8. Now let's make ourselves a note here that you want to memorize this. No matter what you're working with, the probability of at least one is going to be 1 minus the probability of none. So anytime you see this, that's what you're always going to remember. Now let's add a new layer of complexity. If each question was worth 1 point, what are the possible scores you could get and the probability of each possible score? So we listed out all the possible outcomes, but now let's look at the score. If I was to look at this outcome, let's say this one right here, wrong, right, right. Do they care if it's wrong, right, right, or maybe wrong, right, wrong, or wrong, wrong, right? Do they care about either of those, of which one it is when you just tally up your score? No, we don't really care which one you got right or wrong. We just care about the total number. So again, looking at our list, what are the possible numbers of questions you can get right? What are our possible scores? Our score should be able to range from 0 to 3. So I could have scores from 0 to 3. Now let's write down the outcomes that correspond to each of these scores. So if you want to get a 0, you would have to have wrong, wrong, wrong. And the probability of that would just be 1/8. Let's say you want a score of 1. To get a score of 1, you could have right, wrong, wrong, or wrong, right, wrong, or wrong, wrong, right. Any of those possibilities will give you a score of 1. So what would the probability of this be? There are 3 different things that give you what you want, or you can think of it as 1/8 plus 1/8 plus 1/8 gives me 3 out of 8. And for 2 right, you could have right, right, wrong, or right, wrong, right, or wrong, right, right. And again, it would be, there's 3 of them, so 1/8 plus 1/8 plus 1/8 gives me 3 out of 8. And to get a score of 3, you have to do right, right, right. That's only one possibility, so 1 out of 8. So we started with all 8 possible outcomes, and then we changed it to, well, let's just look at the score, and we can kind of condense it now. So we have scores of 0 to 3 and the probability for each one. And that actually finishes us off with another section. So any questions or thoughts here? So you'll notice we do very simple events. We start with tossing a head and a coin. And then we just kind of keep adding on a little more complexity. In section 1.3, we learn how to combine different events. We'll start with what we call intersections. So the event A intersect B, so look at this nice little symbol. Looks like an upside down U. We call this the intersection of events A and B. So and is always for the intersection. So as you're going through these problems, I always say, what word would come out naturally? If you were going to write this in a sentence, would you use the word and, or would you say or? So we're going to talk about ands first. So A intersect B is all the outcomes that are in both A and B. So it has to be in both of them. And so then the probability of A intersect B would be the probability that A and B occur at the same time. in probability classes, we like Venn diagrams. If I was to do this in a Venn diagram, and I'd say here's A, here's B, what would the intersection look like? The intersection would be the part where they intersect, okay? Or where they're both happening at the same time. Now in this diagram, I did assume that A and B overlap. There are times where you'll get things that don't overlap. So you might have situations where here's A and here's B. Do they overlap at all? No. So in this case, there would be no intersection. And that's okay. Again, you have situations where they don't overlap. There is nothing in common. So to illustrate intersections, let's talk about using a standard 52 card deck. And I always assume people know what's in this, but I actually didn't know when I first started taking statistics classes. So if you don't know, you can have either red or black cards. Red cards are divided into hearts and diamonds. And the numbers on the cards range from 2 up to 10, and then you also have Jack, Queen, King, Ace. Most of you probably do know this, but sometimes it's easier to see it written out. Okay, again, diamonds go from 2 to Ace, etc. So let's find the probability that it is red and a Jack. So we're looking for the probability that it is red and a Jack at the same time. So you come up to your table and say, okay, which cards up here are red and Jack? So I could get a Jack of hearts or a Jack of diamonds. So there are 2 red Jacks. There are 52 cards total, so 2 red Jacks gives me 2 out of 52. Now sometimes people ask me, should we simplify these fractions? No, you don't have to. Sometimes we'll simplify if we just want to see if 2 different fractions are actually equivalent, if they're equal to the same thing. But for the most part, I actually like to be able to compare different probabilities if they all have the same denominator. So I usually won't simplify, and that is just fine. You don't have to. So let's now find the probability that it is black and a number card. So probability of black and a number. So black would be the bottom 2 rows, and you want numbers, so 2 through 10, 2 through 10. It looks like we have how many possibilities? I'd say 18 possibilities out of our total of 52. And to find the probability that it is black and a hearts card. So I'll go ahead and wait for you guys to tell me what is the probability that it's black and hearts at the same time. Okay, 0, because you cannot possibly be black and hearts at the same time. This equals 0 because it is impossible. There is no way to be black and hearts at the same time. Or you could say there is no intersection. Or no black hearts. And in our next example, we just have some more Venn diagrams. Let's shade the Venn diagram for each event and find the probability and write our events in words. Okay, so in those, each dot has a probability assigned, so some dots are in our total sample space, some are in A, some are in B, some might be in both. So for A intersect B means A and B both happen. And I usually kind of like to say at the same time. So which things are in A and B at the same time? Well, just the stuff here in the middle where they intersect. So the probability of A intersect B, just add up all the probabilities that are there. So 0.13 plus 0.07 is 0.2. That was simple. But let's look at number 2. So now let's have A intersect B complement. So this means A happens and B does not happen. So where would you shade this? So one of the things that sometimes helps is say, okay, let's shade A first. So here's A. A is everything in here. And if we were to shade B complement, it would be everything that's not in B. So not in B would be all of this stuff outside of B. Okay, so where did those two things overlap? It's difficult to describe in words, but if you were to give it a shot, where are they going to overlap? I need to fill in A, but do I fill in this little part of A that also overlaps with B? No. Okay, so fill in all of A except for what also overlaps with B because we don't want B to happen. Okay, so the probability of A happening and B not happening. Okay, let's see, so what's in there? We have a 0.15 and a 0.18. So that's 0.33. Let's see, number 3, one of my favorite ones, A intersect A complement. So what would this mean? This means A happens and, emphasis on and here, and then what does A complement mean? A doesn't happen. Now let me ask you, how can you have A happens and A doesn't happen at the same time? You can't, right? This would be impossible. Okay? Or A would be everything inside of, well, A, and A complement would be everything outside of A. And do those overlap at all? No. So there is no intersection, no overlap. It's impossible. And what's the probability of impossible events? It's just 0. Okay? Or there's no overlap, there's nothing to count up, so 0. Oh. I think number 4 accidentally got changed because that doesn't sound very exciting. Okay, what is the probability of A? Apparently is what I wrote. Let's go ahead and fill that out, although that's not very exciting. So probability of A would be everything in here. So 0.18 plus 0.15 plus 0.13 plus 0.07. I don't have this one written down, so give me a sec. .53. Let's see. So what do you notice? I guess I did actually want to do number 4. I forgot. Okay, so number 4 here, the probability of A is 0.53. For our next question, what do you notice if you have A intersect B? Okay. Notice, what did we shade there for A intersect B? We shaded everything right here, right? Okay. And what did we shade for A intersect B complement? We got everything right here. What do you notice if you put those two things together? We would be at A, right? And if you do the probability of A intersect B, which is 0.2, and the probability of A intersect B complement, which is 0.33, what do those add up to? 0.53. So the probability of A intersect B plus the probability of A intersect B complement was 0.2 plus 0.33, which equals 0.53. That's equal to the probability of A. Okay, and do you think this is a coincidence? Okay. No, from what we saw up above, that's going to happen every time. Because if you have, not very pretty, here's A, here's B. A intersect B will be this part, and A intersect B complement will be this part. And no matter how they are, you're always going to just end up with, if you put them together, just the probability of A. Now you'll notice as you read your textbook, they have tons of facts like these where it's tons of Venn diagrams. I don't expect you guys to memorize these. I expect you to be able to kind of draw it out and try and figure it out yourself, because there's way more here than you'd actually really want to memorize. In this section, we've been talking about intersections, and we'll also talk about unions. But here in intersections, let's talk about some kind of nitty-gritty details. And I don't expect you to necessarily memorize all these, but you should be able to figure them out. So if I asked you, you should be able to tell me what they should be. So this one is A intersect B. So let's draw a picture here. Here's A, here's B. If we look at the intersection, it would be this part in the middle. Okay, now it's saying it should be equal to, it would be the same thing, so we still have A and B, as if we did B intersect A. And in this case, it doesn't matter which one you say comes first, the intersection is still the part in the middle. And if you happen to have a situation where you have A and B and they don't even overlap, well, the intersection would then be nothing. And again, it doesn't matter which that you say comes first. Okay, our next one is A intersect S equals A. Now remember, S is your entire sample set. So here's my S, here's an A inside of it. If we do A intersect S, well, where do the two overlap? Where do they meet? They overlap here, or they overlap everywhere that A is. So we would get back to A. In our next one, we have A intersect A complement. Well, to find A complement, or first to say, okay, here's A, then A complement is everything outside of A. So here's A complement. Where do they intersect? Where do they overlap? They never overlap, so you get back to the empty set. Let's say A intersect A. Well, here's A. I can't draw another A. This is A. So here's A. Here's my other A on top of it. Where do they overlap? Well, everywhere inside of A. Let's see an A intersect the empty set. Well, they never overlap because there's nothing in the empty set, so you're just back at the empty set. Okay. And our last one, notice we have three different events, A, B, and C. A, B, and C. And notice they're just changing the parentheses, so they're saying let's group B and C together first and see where they overlap, or let's group A and B first and see where they overlap. And it doesn't matter. You can do them in any order, you can group them together in any way. You're not going to get different answers. So let's come back. And I realized I was thinking we finished the section, but we didn't quite. We still have more in this section. Okay, so this is still section 1.3. So first we're going to talk about what we call mutually exclusive events. So A and B are mutually exclusive if they have no outcomes in common. Or you can think of it, I usually say they can't happen at the same time. Okay. And that means that if A and B are mutually exclusive, what would their intersection be? If they can't happen at the same time, or they have nothing in common, there is no intersection. Okay, this is called the empty set. If you're familiar with that from other math classes, it means there's nothing in the set. Okay. Or they have no intersection, and the probability of the intersection would be 0. Okay. And this is always going to look like a Venn diagram if you have A and B and they're going to be separate. There's nothing in common. Okay. And also sometimes called disjoint. So I might also call them disjoint accidentally without thinking, and that's what I'm talking about. So this could be something like someone is a boy and a girl at the same time. Generally speaking, that's impossible. They do not intersect. So that's one thing. The next thing we're going to talk about is unions. So the event A union B, notice that it's just like an intersection, but turn it's the right side U. I would remember U for union, that looks like a U. So it's the union of A and B. It's the event consisting of the sample space outcomes belonging to A or B or both. Okay. So again, when we do the union, it's A or B or both. And so union is always going to be the word or. Okay. If we were to draw Venn diagrams, here's A, here's B, how would you shade the union? The union is everything in A or B or both. So that would be your union there. Now you can also have events that are disjoint or mutually exclusive. So here's A, here's B. What does their union look like? Well, you shade everything in A, you shade everything in B, and you shade everything in both. Is there anything in both? No. So let's shade our Venn diagrams for each event and find the probability. Write the event in words. So A union B means A happens, or B happens, or both happen. And so we go through and find everything in A. So A would be everything here. Okay. And so let's add those up. So probability of A union B. So we'd have 0.18 plus 0.15 plus 0.13 plus 0.07. Okay. And then we do everything in B. So 0.11 plus 0.02 plus 0.09. Now, should I add on the 0.13 and 0.07? What do you guys think? Okay, so we only need to do it one time. Otherwise, we would be double counting, and we don't want to double count it. So that 0.13 and 0.07, that's in the intersection. We only need to have it in there once. Otherwise, we'd just be counting it more times than we truly want to. So if we add these together, we should get 0.75. And we didn't truly shade it, so the shading would be everything in here. And A union B complement. So that means A happens, or B doesn't happen, or both. So this one gets a bit interesting. So let's say, okay, so we want A to happen. So A would be everything in here. So 0.18 plus 0.15. Now, let's kind of leave this 0.13 and 0.07 for a second. Now, let's look at what is B doesn't happen. So B doesn't happen would be everything outside the B. Okay. So everything outside of B is 0.08, 0.01, plus 0.16. Okay. And actually everything outside of B would also be these things in here. Do I need to do the 0.18 and 0.15 again? No, we're never going to double count things. Okay. Now, my final question to you is, should I include these? What do you guys think? The 0.13 and 0.17.
No, because they're part of B.
Okay. And anyone think anything else?
In order, so yes, because it's not just limited to B not happening.
Okay. And you're right there. So because it says an or, it says we want A to happen or B to happen or both. Or, sorry, B to not happen or both. And because it's an or and it's not actually an and, you can still include these because these are part of the A. And as long as it's part of one of the things we said, we want it. So in this case, we are actually going to add the 0.03 and 0.07 because it was part of the A. So if we were to shade, again here, everything that we've included, everything that's in A, or everything that's in B, or both. So we've got almost everything there. And again, this intersection was included because it was part of the A. So ors are a little bit different there. And 3 is going to be kind of similar here. I like 3. So this is A union A complement. So this means A happens or A doesn't happen. Or both. Okay. So for A happening, that would be, okay, everything in A. Okay. And what's A complement? Or A doesn't happen would be everything outside of A. So by the time you have either A happens or A doesn't happen, what are you left with? Or what do you get? You should have everything, right? Either A happens or A doesn't happen. That's all your possibilities. So you'd have a probability of 1. Now, is there anywhere that both happen at the same time? No, but that's okay. You'll often get things where both can't happen at the same time. As long as you have A happens or A doesn't happen, we're good. And now, for our final one, this one is a little bit tricky as well. Let's do A complement union B complement. So this is A doesn't happen. Or B doesn't happen. Or both. So for A doesn't happen, this is everything outside of A. Now for B doesn't happen, that would be everything outside of B. Now for a union, as long as something's shaded somewhere, we're going to count it. So we want either A doesn't happen or B doesn't, or both. So we actually here have everything but what? So this is everything but A intersect B. That's kind of an interesting little fact there. So we shaded everything but B, A intersect B. And so I would actually then kind of use a shortcut. So if I want the probability of A complement intersect B complement, I'm going to do 1 minus the probability of A intersect B because I don't really want to add up all of those numbers. I'll just say, okay, it's everything but this, so let's subtract out the but part. So 1 minus 0.13, what's the 0.07? Which is 0.8. Now in your homework, you will try a few of these different Venn diagrams, and it's kind of this, play with the logic, get used to doing it. They're not little facts that I actually expect you to memorize. Okay. And as part of that video, I said I made a video for all of those intersection facts. I also made a video, it's the same video for the union facts as well. So now we've talked about unions. And remember, a union is an OR. Okay, so it's wherever we have A or B or both. So let's remind ourselves, A or B or both. If you're talking about A union B. So A union B means A or B or both. Okay. So if we have A union B equals B union A, that just means it doesn't matter which order you say it in, you get the same answer. Okay. And A union the empty set, well, so it's A or the empty set or both. Well, the empty set has nothing in it, so A or nothing or both. There's nothing in the both part where they overlap, so you're just back at A. And A or both would again just give you A. Let's go ahead though and look at A and A complement. Okay. What happens if you put the two of them together? So we shade everything in A. We also shade everything in A complement, or both. There's nowhere that they overlap, so there's no both. But notice we've gotten everything in the original sample space of S. And if you do A union S, which is the entire sample space, you have everything in A or the entire sample space, which just gives you your entire sample space. And again, finally in the bottom, again, it doesn't matter if you change the order or you change which ones you group together first, you'll get the same results. And now, let's go into the more interesting practical things. Let's learn about the general addition rule. So if you want to find the probability of the union, okay, you'll do the probability of A plus the probability of B. Okay, now let's draw a diagram here. So you'll do the probability of A. Well, that would be everything in here. Okay, so we did the probability of A. Then you'll do the probability of B. So that's everything in here. But what's our situation here? What's the problem with adding everything in A and then adding everything in B? So someone go ahead and tell me what was the problem here.
Exceed 1?
It's going to exceed 1, and why?
Because you're double counting.
Okay, we're double counting the intersections, so probability of A plus probability of B double counts the intersection. So if you're writing a formula, you add both of them together and then you take out that intersection once because we double counted it. So now let's talk about, okay, so that's nice. We take out the intersection, we double counted. What if there's not an intersection? What if they're mutually exclusive like this, and there's not an intersection? What would the probability of A union B be? So go ahead and tell me.
It's just the probability of A plus the probability of B.
Okay. Yeah, you don't have to worry about taking out the intersection because you didn't double count it because it's not there. And really, you might be worried about, okay, now I have to memorize another formula, and I don't want to memorize two different formulas. But if you memorize just your general formula, probability of A plus probability of B minus the probability of the intersection, and let's say you forget and you start writing out this long formula, and then you get to this intersection part, you're like, oh wait, there's not an intersection, so what's the probability of the intersection if there's no intersection? 0, and subtracting 0 doesn't change anything. So really you only have to memorize one formula. And as far as mistakes that people make on the exam, one of the biggest ones is usually you forget to subtract that intersection. So just don't forget that. let's try it. This one actually seems probably the most real life we've done so far. Let's say we have a certain company. 15% of our employees have managerial positions. 25% have MBA degrees. We also know that 9% of the employees are managers and have MBA degrees. Now, as far as what you do in the class, okay, this is kind of our first story problem. When I read story problems, I always sit down and say, what information did they give me first, and write it down. So they have 15% of employees have managerial. So I say something like the probability of, I'm going to say man here for managerial, that would be 0.15. If you prefer, you could use percentages, but I don't like doing calculations with percentages because then sometimes you start messing up if you have to multiply or things like that. So I usually change it all to decimals. Okay. And 25% have MBA, so that would give us a probability of MBA being 0.25. And 9% have both. So the probability of manager and MBA equals 0.09. And I'll usually do all that before I even look at the questions. Okay, now first question, what is the probability that manager intersect MBA? Okay, well, we actually just found that. It is 0.09, right? Because there are some people that have both. And I might ask you, are the events manager and MBA disjoint? Or mutually exclusive, and why? Okay. Well, we just looked, are there some people that are both managers and have MBAs? Yes. So they are not mutually exclusive because some are managers and MBAs. Okay. Also, the probability of manager intersect MBA is not equal to 0. If they were disjoint, the probability of the intersection would have to be 0. But it wasn't 0, it was 0.09. And now, let's find the probability of manager union MBA. So the probability of manager union MBA, well, you start and you add the probability. So you do probability of manager plus probability of MBA, but then you say, wait, that's going to double count them, and you subtract the intersection. So we wrote down all those probabilities up above. Manager is 0.15, MBA is 0.25, and there were 9% or 0.09 that were both. And so this gives me 0.31. So you'd have about a 31% chance of getting a manager or an MBA or both. Let's see. Our next one, according to the MBA or M&M website, the color distribution of M&Ms is 24% blue, 16% green, 20% orange, 13% red, 14% yellow, and 13% brown. Now, in this situation, are the events blue and orange mutually exclusive? And why or why not?
Because you're not going to pick out one of them.
Okay. So, yeah. So, yes, they are mutually exclusive because we're not going to have blue and orange at the same time. Now, when you're doing things like this, we're assuming that they don't have any production errors and one comes out with two colors, or it's not any specialty things. These are just all either blue or green or orange. You don't have anything that are both. So let's find the probability of blue union orange. So the probability of blue union orange would be the probability of blue plus the probability of orange. And do I need to worry about subtracting the intersection? Is there going to be an intersection? No, because they are mutually exclusive, so we don't have to worry about that. So the probability of blue is 24%, so 0.24. Orange is 20%, so 0.20, or 0.44. Again, I prefer decimals. You can do percentages if you want, but decimals are just kind of a little bit nicer for us. And 19, let's find the probability that a reader subscribes to the Atlantic Journal or the Beacon News. So this is kind of a nice little two-way table. We have people that are in the Beacon News, people that are not in the Beacon News, Atlantic Journal, not Atlantic Journal. So if we want Atlantic Journal or Beacon News, so Atlantic Journal or is a union, Beacon News, we'd say, okay, let's find the probability of Atlantic Journal plus the probability of Beacon News minus the probability of the intersection. And how are you going to find these probabilities? So for Atlantic Journal, you say how many people read the Atlantic Journal. So the Atlantic Journal is everything on the first row. So there are 650,000 people that read the Atlantic Journal out of a total of 1 million. And for Beacon News, there are 500,000 people that read the Beacon News. Now, how many people read both? There are 250,000 people that read both, and we don't want to double count that. And so this will give me, you put it all into your calculator, and you're going to get 0.9. Now, is there another way you could have done this problem? If you just wanted a Atlantic Journal, Union, Beacon News, or both, you could have just gone through and said, who reads at least one of these two? This person, this group, reads the Atlantic Journal. This group reads the Atlantic Journal. This group reads the Beacon News. This group reads the Beacon News. Could you just add up those three numbers? If I just added up those three numbers and divide by 1,000,000, I would still get 0.9. So when it is individually listed, you can just go through and circle everything you want and add them up. If you're just dealing with numbers, then you'll do everything for the first, everything for the second, and subtract out the intersection. So lots of times there are multiple ways you can do something like this. Now, could you have a time where you have 3 events? So let's say you have A, B, and C. If you want your union, you do everything in A, everything in B, and everything in C, right? So we'd add up everything in A, and then we'd add up everything in B, and then we'd add up everything in C. Now, do you see any problems here? There's going to be lots of double counting, right? Okay. And so we say, okay, I double counted this part, and this part, and this part. And so you subtract all of those back out. Okay. So you can see we have A plus B plus C minus each of those intersections. But then at the very end, you're like, okay, I double counted all of these things, and you subtract them all out. But it turns out, if you subtract them all out, then you actually don't have this little piece in there anymore because you subtracted it out so many times, so you add that little piece back in. This isn't a formula I expect you to memorize, but you might use it once or twice on your homework. Just know that it is there. If you need it, you add up all of the events, you subtract out the 2-way intersections, and add the 3-way intersection back in. But you can go look it up and do that. Whereas if you have a bunch of mutually exclusive events, you don't have to worry about the intersections. They don't have any intersections, so you just add up all of the individual probabilities. Now there is something called a partition of a sample space. And what this means is you start with a sample space like this of here's S, and you start dividing it up. And so this could be like A1, and this piece could be A2, and this piece would be A3, A4, A to the 5, A to the 6, A to the 7, A to the 8, etc. Okay. So our partition is you divide it up. Now the important thing for a partition is that nothing is double counted, or there are no intersections. So any outcome you pick, if you pick an outcome here or here or here or here, each outcome will only be in one event. Okay. So to do a partition, you just divide it up into mutually exclusive events. This is something that we kind of see theoretically here and there. It's not going to make a big difference to you. You're not really going to use it much. It's just kind of that theory. And so we have finished the section here. Any thoughts or questions? So 1.4 is conditional probability. And this one you usually have to pay attention to a little bit closer. It's not quite as intuitive. So let's say if we know that an event B has already occurred, then the probability that A will occur, we're going to write the probability of A given B. Okay. And so we read it A given B, so this B is always the part that is given or has already happened. Again, this is tradition. The person that invented it said we'll write the thing that has already happened second. And we'll use this nice vertical line in between. So again, it says we already know that B has happened. Now let's find the probability of A. So we could also say it's the conditional probability of A given B, or we could say it's the probability of A conditional on B. So how do you find conditional probabilities? Okay. Or what would this truly mean to us? Let's start with an example. We can use some logic here. Let's find the probability that a household subscribes to the Atlantic Journal given they read the Beacon News. So we know they read Beacon News. And what this means for us is if we know that they read the Beacon News, we only care about this. Do we care about this column anymore? No, we really don't care about it. You kind of throw it completely out. And your whole world narrows down to the Beacon News. And so we can reduce our sample space. And this is very practical. There are lots of times where you know something, or something is given, and now you're looking for probabilities with that additional knowledge. So we know they read Beacon News. We only look at Beacon News. What's the probability that they read the Atlantic Journal? So probability for Atlantic Journal given Beacon News, you should say, okay, the Atlantic Journal, there are 250,000 out of a total of 500,000. Again, those numbers are smaller than the total million because we reduced our sample space. We know they read the Beacon News, so that's all we care about. Or let's find the probability that they subscribe to the Beacon News if we already know that they read the Atlantic Journal. So now we're looking for the probability of Beacon News if we already know that they read the Atlantic Journal. Now, do you think that these two probabilities will be the same? Okay, they're not going to be the same. And so that means you have to really pay attention. That's one of the hardest things, is just keeping track of which one do you write first and making sure you really pay attention. So if we know they read the Atlantic Journal, that's the part that's given. So that means you reduce your sample space and we only care about that top line. Our whole world has been reduced to that. So now what's the probability that they read the Beacon News? There are 250,000 people that read the Beacon News out of a total of 650,000, which is 0.38. Again, because we knew they read the Atlantic Journal, we only looked at the Atlantic Journal numbers. And we don't care about the rest of the table. So let's look at a few others with just logic. So if we're talking about a fair six-sided dice has the numbers 1, 2, 3, 4, 5, 6, what's the probability of rolling a 6? Probability of rolling a 6 would be 1 out of 6 because there are 6 possibilities. Now let's complicate though. Let's say we rolled a six-sided fair dice and your friend peeks and tells you that it is an even number. Now what's the probability that you rolled a 6? Okay. So even numbers are 2, 4, and 6. So if you know that it's even, now what's the probability that it's a 6? So someone go ahead and tell us here. Okay, 1/3, right? Because there are only 3 choices now. So the probability that it's a 6, if you already know it's even, is 1 out of 3. Now let's say you roll the dice and your friend tells you it's an odd number. Now what's the probability that you rolled a 6? With odd numbers being 1, 3, and 5. So what's the probability of a 6? 0. Probability of 6, if you already know it's odd, would be 0. Now we did these problems just by reducing our sample space. We said we don't care about all the numbers, only the even numbers, or we only cared about the Atlantic Journal. Okay, but now we might have more complicated problems, which means we need a formula. So it turns out we do have a nice little formula here, which is the conditional probability formula. So the conditional probability that A will occur, given that B has already occurred, okay, is going to be the probability of the intersection divided by the probability of what you know happened. Okay. So this probability that goes on the bottom is always the probability of the given. Or the probability of what already happened. Now, mathematically, if we're doing this formula, what do we have to assume? Can you divide by 0? No, and so we always assume that the probability of B is not equal to 0, otherwise we're going to have mathematical problems. So again, we'll do the probability of the intersection over the probability of what was given. So we can practice that. Let's write the formula the other way. So the formula for the conditional probability that B will occur given that A has already happened. So this means A has already happened and we're looking for the probability of B. So you would start by doing the probability of the intersection over the probability of what you know, which in this case would be A. Or notice it's the second, whichever letter comes second is always the one that goes on the bottom. So I like to think of it as the probability of our unknown given what we know is always going to be the probability of the intersection over the probability of what we know. Let's put it into play. Let's say that the probability of having clouds and having rain at the same time is 30%. Now the weatherman says that the probability of it being cloudy today is 70%. If I look out the window and it is cloudy, what's the probability of rain? So let's write down what they've told us. The probability of having clouds and rain at the same time is 30%. That's the intersection, right? So probability of clouds and rain is 0.3. Let's see, the probability of it being cloudy is 0.7. Now, if I look out the window and it's cloudy, what's the probability of rain? So this is telling me I know something. I know it's cloudy. So that's the given, and I want the probability of rain. So probability of rain given cloud is going to equal probability of the intersection over probability of what you know, which is that it's cloudy. Okay, so the intersection is 0.3. Cloudy is 0.7. This should give me 0.428. Now this is a place where it's really good to double check. Did I get a number between 0 and 1? Yes. If you didn't, that's a really good sign you did something wrong if you get a number bigger than 1. Okay, so again, it's kind of that probability of I know it's cloudy. That kind of changes the probability that it might be raining. Now I've noticed some people kind of go through and they just say, I'll just put the extra probability that they gave me on the bottom. You can't always count on that. Okay, actually pay attention, make sure you put the probability of the given part on the bottom. So what I actually want you to do now is take the next 5 minutes and do as much as you can on the next example. And then we'll go through it together.